Hello everyone, this is DSS Zindabad and today we are going to discuss the daily challenge of Leetcode, which is K inverse pair array. So let's jump into the problem statement. For an integer array nums, an inverse pair is a pair of integers I, j, where I is greater than equal to 0 and it is less than j and j is less than the length of the array that has been given to us and the number that is present on the index I, which is lesser than j, index j, is greater than nums of j. Given two integers n and k, return the number of different arrays consist of numbers from 1 to n such that they are exactly k inverse pairs. Since the answer can be huge, you can have to take a modulo. Okay, so after reading the problem statement, we understand that we'll be given two parameters, that is n and k, right? So basically, k denotes the number of inverse pair the array can have, and n denotes the numbers in an array. So basically, you've been given an n and the array will be containing numbers from 1 to n and n is inclusive, right? And what you have to do is you have to find the inverse pair. So what is inverse pair? Let us suppose that n was 3 and k was 1, right? So if n was 3, that means I'll have an array and that array will have elements 1, 2 and 3. So my array has these elements and I have k is equals to 1. That means I need to have the number of inverse pair in that particular array as 1. So this basic array can have different kinds of permutations, right? So what are permutations? Permutations is when I change the places of the elements that are placed, right? So I have 1, 2, 3. I can have something like 2, 1, 3. I can have something like 3, 2, 1. I can have something like 3, 1, 2, right? Or I could have something like 2, 3, 1, right? And there can be some more. Basically, this exactly depends upon that I have three different places, right? And I have three elements that I want to place. So for my first position, I can choose any of these three elements. Let us suppose these three elements were A, B, and C. So on my first position, I can either keep an A or a B or a C, right? Suppose I kept, so that means for this one position, I have three options, right? So once I have put something here on the first position, I'll simply erase it from my given elements that are needed to be placed. Now I have just two elements. So for my second position, what I can do is I can place any of those two elements. So permutation means number of combinations that I can have, right? So suppose you have placed one element here. You just have one element here, that is 1. So this represents 3 factorial, which is 3 into 2 into 1, which is 6. So that means for this array, which has elements from 1 to 3, because n's value is 3, right? So it can have 6 different combinations in which these elements can be placed on different indexes, right? Okay. I suppose this part is clear. Now let's talk about how are we finding the number of different arrays. For finding the number of arrays which have k inverse pairs, what I'll do is I have these array, right? Then I can figure out what is the inverse pair. See, basically suppose you have something like 2, 1, 3. Now, when we talk about an inverse pair, there are two conditions it needs to follow. The first condition is that I is less than j. So I and j are, these are the indexes, right, in the array. The second is that the num of I, that means whatever is placed on the ith index, is greater than whatever is present on the jth index, right? So if you look at this combination for this given example, so you can see that 0 is less than 1, right? But if you see num of 0, that is 2. And if you see num of 1, that is 1. So you can see 2 is greater than 1. So as it is satisfying both of these conditions, hence it is an inverse pair. Okay. And now what we want is that we were given this basic array, right? We understood that from the given set of elements, that is 1, 2, 3, because n was 3, I can have n factorial combinations, which means I can have 6 combinations for this example. And supposedly, if I'm discussing this, right? So I have understood that this is one pair where I have got an inverse pair, right? Similarly, you can have a comparison for 1 and 2. So you can see that 1 is less than 2. And if you see that num of 1 is 1, but num of 2 is 3. Now you see 1 is not greater than 3. 1 is less than 3. So hence it is not an inverse pair. So from this given combination of array, that was 2, 1, 3, I know that I have only one inverse pair, right? So for this combination, my answer will be that yes, you have to include it. So if you are finding something that has n is equals to 3 and k is equals to 1, so in that case, you can include this array. I hope the problem statement is clear. Now let's talk about the approach. So when we talk about the approach, see, the brute force approach that you can think of is something you could have got till now, as I explained what the problem statement is. So basically what you can do is you've been given something like n, right, which is representing the elements in the array in the range of 1 to 3, 1 to n, sorry, right? So, and you've been given something like, you have been given something like an k, which is denoting the, what should be the number of inverse pair in a particular array, right? So what you can do is you can say that from this I can have a very brute force approach wherein I am generating all the possible permutations corresponding to n, right? So I'll be generating all the possible permutations corresponding to n, and after generating these, I'll be traversing and checking if a particular permutation is an inverse pair or not. So suppose it's a yes, in that case, you can increment the count or whatever variable that you'll be finally reducing as an answer. Or if it is a no, then you can go to the next permutation, right? So if I do something like this, let's try doing it once. So I'll be taking the same example where n is 3 and k is 1, right? So when I have this, I can have 6 different permutations, right? So when I can have 6 different permutations, it can be something like 1, 2, 3, right? I can have something like 1, 3, 2. I can have something like 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. These are the possible combinations that can be formed. Now here what I'll do is after forming these permutations, which will take a time complexity of O of n factorial. Why? Because we know whenever we talk about permutations that we just saw when I was trying to fill in the places in that example above, we saw how permutations are calculated, right? So after this calculation, I'll figure out the value of k for each permutation, right? So here, if you see that here we do not have any inverse pair because the two conditions, that was I is less than j and num of I, that means whatever is present on the ith index in num is greater than whatever is present on the jth index num. This is not satisfying for the first permutation we have, right? So k is equal to 0 and I want k is equal to 1. So it will not be added. Then I'll again traverse over it, and here I can see that yes, this is a combination that k is equal to 1, right? So I'll be like, okay, have something like a count variable which is initialized to 0, it becomes 1. Now for this, if you see, you have 2, 1, 3, right? So here again, we have something where k is equals to 1, right? So count gets incremented. Now you have 2, 3, 1. As you can see, you have 2, 3, 1, right? So 3 is greater than 1 here, right? So you can again have something, you can consider this permutation, right? And so on. So this is how we'll be doing it. But if you look at it, the time complexity is O of n factorial into n square. Why? Because you have to be traversing over all of these elements. That is, if you have something like 2, 1, 3, right? So what happens is, if you are standing here, you have to figure out that if is there any index. For example, I here is 0. So j will range from I plus 1 to n, right? So you have to have two nested loops to figure out and check for these conditions. So you will have a time complexity which is very, very huge, right? So what we need to do is we need to figure out some way so that we can boil down this time complexity. Now, let's talk about how are we going to do it. So basically what we'll be doing is, let's try figuring out the patterns, right? I've understood that if I want to create all of the possible permutations and then figure out, it has a very high time complexity. So I'm like, let's see what happens if I am doing it manually. That means, suppose n is 4, right? When n is 4, that means I'll have something like these different ways of basically putting everything together, right? So that means just for my first element, right, I have these 4 ways I can do it, right? Because from this, I know I have to put 1 to 4 in these dashes that I've made, right? So let us assume I have something like a 1 here, right? That means on my 0th index, I am putting a 1 here. For this case, for my 0th index, I'll put a 2. For this case, I'll put a 3. And for the last case, I'll put a 4. So see, if I put a 1 here, right, I am not considering that what is the order of this section. Okay? So it means I do not care about the order of this section right now, as of now, right? I do not care about this section right now. I'm just concerned with this, right? I'm just concerned with something like a base condition. So if 1 comes here, then I know that the k will always be 0. Why? Because I know that the array can have 1 to n, right? N inclusive. So the minimum value that is less than 1 is 0, but it is not in the range. So that means I'll never have an inverse pair. Why? Because for having an inverse pair, the condition that we require is that I should be less than j and num of I should be greater than num of j. But for this case, it will just for 1. I'm not talking about this section. Just for 1, we'll have k is equal to 0. Now, if on the 0th index, I'm keeping a 2. See, I have to figure out these later. But let's just talk about 2. So as you know, from 1 to 4, I know 1 is less than 2. So at least for these 3 indexes, at least at one place I have to keep a 1, right? So therein I'll have just one inverse pair. Okay, I hope now you're getting the intuition. Similarly, if we have a 3 here, so from 1 to 4, 1 is less than 3, 2 is less than 3, right? So from these 3 positions, at least at 2 places you can keep it. So you can have 2 inverse pairs. And similarly for 4, you can have k is equals to 3, right? So now we have just had used permutation to visualize how things are really happening and to directly use end in case. So see, when I talk about something like this, as here I am just figuring out the base case. I'm saying I do not care about it right now. I mean, later I might care about it, but right now I don't. So this is similar to what? It is similar to recursion, right? Wherein we say that just figure out the base case, rest will be sorted out itself. So here I can see that for this part, my n gets decremented by 1, but my k remains as it is, right? Why is this happening? Because I have figured out one index, but my k is 0. For this part, n gets decremented by 1, but now my k is 1. So we can have something like k minus 1. For this part, it is n minus 1, k minus 2, and here I am pretty sure you've got it till now, k minus 3. So here what you observe is that suppose, right, here, because I had something like n is equals to 4, so I had this condition till here. But suppose we had something like n only. So in that case, what we can do is we can have n minus 1 and k minus I, where I is looping from 1 to n, right? So this is my recurrence relation that I will be using, and I'll be using a for loop here. I hope you've understood why I did what I did. Now let's quickly code this up, right? Let's write the recursion. It will have a very high time complexity, agreed. Then we'll talk about how we'll optimize it and all of it, right? So now let's jump into coding it. Okay, so this is the problem statement. Let's have something like a solve function, right? And in that solve function, I'll be passing just the given n and k. Okay, so the solve function will be of int type, right? And let's just quickly copy paste this there. So now what we'll do is, we know whenever we talk about recursion, right? So we have to divide recursion into the base case, exploring all the possible actions we can take upon the given problem, and the recurrence relation. Okay, so here what will be the recurrence relation? So what we can do is we can have something like an int answer, right? And we can run a for loop, right? So herein, as I told you, int I is equals to 0, I is less than whatever is the current value of n, I plus plus, and herein I will say answer plus equals to solve. What was the recurrence relation we found? That was n minus 1, k minus I. And then, as here it is given that we might have very big answers, so you can have something like int mod as 1e9 plus 7, and you can take a modulus here. So it can be answer is equals to answer and take a modulus with it, and then you can finally return whatever is the answer, right? Why are we adding it all? We are adding it because we have to find the different number of different ways, right? Now let's talk about the base case. What should be the base case? See, the base case should be when we have found that k has become 0, right? So I can say that if k equal to 0, in that case, you return me a 1. That means I have achieved whatever value of k I required, right? And you'll also need to handle one more condition, that if k is less than 0, right? In that case, what you have to do is you have to return a 0. Now, what does this case mean? It means that for here in the recurrence, as we are decrementing k by I, you might get a negative value. That means you're going to minus 1 or any negative value that is not 0, right? So in that case, it means there is no possible way to have any inversion pairs. I think we're good to go. Let's quickly run it. And we're getting the right answer. I'll submit it. We'll get a TLE, but let's just submit it for the time being. Yes, we got a TLE. So now let's discuss why are we getting a TLE and how to overcome it. Okay, so this was the code that we just wrote, right? So basically here, why are we getting a TLE for bigger test cases? How are we going to optimize it is something we'll learn once we do a dry run for an example, right? So far we've been discussing n is equals to 3 and k is equals to 1. So I'll be having a dry run for this very same example. I'll be drawing the recursion stack space as well as the recursion tree so that it is easy. So basically this function call is made, right? 3 comma 1. So initially I'll draw something here. My recursion stack space has s3 comma 1, right? So it comes here, it checks that neither of the base cases is being satisfied because my k is 1, it is greater than 0, right? So I'll have an answer. So my answer is 0, and for I is equals to 0, the first I go here, I'll say answer that was 0 plus a solve call is made, n minus 1, it becomes 4. Sorry, it becomes 2, n minus 1, it becomes 2, right? 3 minus 1, that is 2. And k minus I, as I was 0, k was 1, 1 minus 0, it remains 1. So now this function call is added into my stack, and this function call s2 comma 1 is being executed as k is still greater than 0. So I'll again have an answer initialized to 0, right? My I remains 0, so it calls for another I is equals to 0, and the answer was, as it was initialized 0, you'll have 0 plus solve n minus 1. Now when you decrement n, what you get is 1, because n initially was 2, so you get a 1, and k minus I, k is 1, 1 minus 0 remains 1, right? So this function s1 comma 1 is added, right? This function call comes here, base condition is still not satisfied because k is greater than 0, and answer variable is initialized to 0. Again, I is equals to, now for I is equals to 0, you come here. So here what happens is, you can see that I right now, sorry, n right now is 1, right? So what happens is, you come here and you will see that you will have answer as 0, right? So herein you will say 0 plus a solve call n minus 1, n was 1, so 1 minus 1, 0, comma k minus I, k is 1, I is 0, so you'll get a 1. So s 0 comma 1 is added here. Now this is basically executed. So neither of the base cases follow, right? Answer is initialized to 0, right? But it will not go in this loop. Why? Because now n's value is 0 for this function. N's value is 0, so it will not go here. It will simply return answer. Answer was 0, so it is returning a 0, right? Now this gets popped out. My pointer is pointing here. What happens is, it says, okay, so you have to recompute it because you've just done it for I is equals to 0. But in this case, I is equal to 0 has been computed, but n's value is 1. So you can only run this loop for I is less than 1 because n's value is 1. So you cannot have another call. That means you've completed its life cycle. Simply return the answer. So it will return a 0 to its parent and it will be popped out. So now we're standing on s2 comma 1, right? So you have computed for 0. You can compute for I is equals to 1 now. So when you compute for I is equals to 1, you will have answer was 0 here. So 0 plus solve call is made. N minus 1, n was 2, 2 minus 1, 1. K minus I, k was 1, I was 1, that makes it 0. This function call is added s1 comma 0. This gets executed, and as it is satisfying the base case, which is k is equal to 0, you will return a 1, right? So now your answer is having a 1, right? So after that, you from this this has been executed, gets popped out, where again on s2 comma 1, another call is made for I is equals to 2. This call will not be made. Why? Because n is 2, right? And you have I is less than n, right? So this call will not be made here. So you've computed all the I values for the range 2. So this gets popped out and it returns an answer 1 to its parent, that is s3 comma 1. This is where the pointer is pointing. It says, okay, you have computed everything for I is equals to 0. Now you can do it for I is equals to 1. So for I is equals to 1, you get S. Again, answer, as you know, was 0, but it got an answer. So answer has become 1 now, right? So here what happens is you'll have 1 plus a solve call is made, n minus 1. N was 3, 3 minus 1 makes it 2. K minus I, k was 1, 1 minus 1 makes it 0, right? So this function call is added into the recursion stack space. It sees it is satisfying the base case and I have to return a 1. So this returns a 1. My answer gets updated to 2. Then another call is made for I is equals to 2. Now I have 2 in my answer, right? Plus a solve call is made. So now you had a 3, right? So it remains 2 because n minus 1 makes it 2, and k was 1, k minus 2 because k minus I for this line, right? So it makes it minus 1. This function call gets added s2 comma minus 1. Now when this function call is executed, this will return a 0. So it returns a 0 and it gets popped out. Where again on s3 comma 1, it has completed its life cycle, it gets popped out and you get an answer as 2. I hope this was clear to you how recursion is working, right? So for at every point you have n different recursion calls, right? So the time complexity is exponential in nature, right? And the space complexity is O of n, where it corresponds to the recursion stack space. Okay, so now let's discuss how can we optimize it. Whenever we talk about optimizing recursion, right? So whenever I'm talking about optimizing recursion, I know one thing, that I have something like overlapping subproblems, right? For this particular example, you might not be able to visualize these overlapping subproblems because n value was very small. But if you take a value of n that's very high, then you will get overlapping subproblems. And to solve that, we use something as dynamic programming. Okay, I have already told you what dynamic programming is in my previous videos, so I'll not be iterating over that fact. And I'll use something as memoization. So what is memoization? It is a top-down approach wherein I'll be using a DP vector, right? And I'll be computing things, storing them, and so I'll be using a DP vector. I'll be computing things, storing them, and rather than refiguring out what it was, I'll be using the stored values directly. So in the above code, to apply DP, what we'll do is we'll simply have something like a 2D DP vector. Why do we have a two-dimensional vector? Because in my recurrence, I saw that n and k were changing. That means two parameters were changing in my recursion function, right? So that is why I have a 2D DP. I'll pass it here, right? And I'll have it here. I'll have a example that if DP of n k is not equal to -1, that means it has already been computed. So use that value rather than recomputing all of these things. So let's quickly go to our code and make these changes and see if it is working fine. So this was the code which had the recursion. So I'll be declaring DP, right? Here in the constraints, you can see that both the values of n and k are less than equal to 1000, right? So I can have something like 1001 for the initial size of these DPs, right? Then I can use a memset function. I'll pass DP, what I want to initialize it with. size of dp, right? As it is global, I do not have to specifically pass it into the solve function, right? I'll have an if condition that if dp of n and k is not equal to -1, that means it has already been computed. So you simply return it, right? Else, at every point of time where you are returning the answer, you store it into the corresponding value of n and k at that point of time. I think we're good to go. Let's quickly run it. Let's submit it. And it is working fine. Okay, so this was the code that we just wrote. This is the DP memoization code, right? So herein the time complexity, which was earlier exponential in the case of recursion, it becomes O of n into k, right? Because we are using something like DP, so there are no recomputations, right? And the space complexity is also O of n into k, right? Because if you see the dp vector, though we have initialized it explicitly, but in the cases according to the problem that is being run, it will vary, right? And you'll also have a recursion stack space alongside this. I hope this problem was clear. If there is any other doubt, you can always comment and we can discuss it. Please like, share, and subscribe. Thank you so much for viewing the video.